Okay, let's start. Hi, everyone. I'm Nicolás Bernal from the Universidad Nariño in Bogotá, Colombia. And today we are super happy to have Josef Pradler from Vienna, from the Austrian Academy of Science, so the Österreichische Akademie der Wissenschaftler, or something like this. He will tell us about direct detection and how to break this no-go theorem in direct detection. So please, Josef. So first, let me remind you that you guys can ask questions via the Q&A system of YouTube to Josef. So at the end of the talk, we'll take all the questions. So please, Josef.
Hi, Nicolás. Hi, everyone. Thanks very much for tuning in. So I have to go to full screen now, right?
Right.
1 second. I have to share my screen. Sorry. Okay. Okay. Thanks very much, Nicolás, for inviting me to give this talk here. So the title of the talk is How to Break a No-Go Theorem in Dark Matter Direct Detection, and it's work which I've done in collaboration with Chris Kovaris from CP3 Origins in Odense, Denmark. And the archive address you can find right here, and we have submitted it to PRL. So I presume this is a very educated audience, but nevertheless, let me sort of start out with a few basics on a few basic facts, which you probably know all very well. So how does direct detection work? So what we are trying to do is we have a dark matter particle from the galaxy coming into our detector, and it scatters on the nucleus here with mass mn. The dark matter goes out with a certain scattering angle, and the nucleus recoils. And so what we're after in direct detection is the so-called recoil spectrum. So that's the rate of recoils as a function of energy, of recoil energy. And this is sort of the simple master formula right here. So NT is the number of target nuclei per kilogram of detector material. Rho over m dark matter is the local number density of dark matter. So that sets the overall rate, and then we have we fold the recoil cross section, which is given to us by particle physics, with the galactic velocity distribution of the WIMP boosted into the frame of the detector. And this factor V here is just to make the number density times V, it becomes the incoming flux of dark matter. And in this business, we measure events in counts per day and kilogram in keV. So this is it gives you a sense that this is a rare event search because we do this per day, and now currently the background's at the 10⁻³ level. So these are really super rare event searches. So experimentally, what do we do once the nucleus is kicked? We try to pick it up in various channels, and here I show you three pictures or cartoons of how this is done experimentally. Either we might directly observe the heat upon the recoil, so the nucleus is kicked, and we can operate a thermometer which is superconducting right at the transition, and so that a small increase in temperature leads a large increase in resistance, and this is something which can be read out. There are also detectors which yield more striking signatures, such as bubble nucleation here in a liquid. The other possibility is to use scintillation. So you can think of this as sort of a wavelength shifter. You're kicking the nucleus, and usually you are depositing keV energy, and what comes out is energy in the optical regime in form of scintillation light. Here you see this blue light. Or we can pick up the ionization, that is the nucleus is kicked, and because of the kick, some electrons fly off, which can then be drifted in an electric field. Sort of this leads to an amplification of the signal, and then there's a delayed ionization signal that can be read out. And very often these detectors use two technologies in order to discriminate electron versus nuclear recoils. Okay, so this field started out with high hopes more than 2 decades ago, when people realized that if we think of WIMP dark matter, really weakly interacting massive particles, as being the dark matter massive with masses in the ballpark of the electroweak scale, so 100 GeVs, and if we interpret weakly as being C-mediated, then the cross-sections for scattering on the nucleon of the dark matter particle on the nucleon on the order of 10⁻39 centimeters squared or 10⁻3 picobarn, and that's this error up here. Now this is the typical plot we will be working on in this talk. So where you see a dark matter mass on the x-axis and the WIMP scattering cross-section, the elastic scattering cross-section on the nucleon, so the sigma n here. And so C-mediated cross-section is somewhere up here, and these lines here show upper limits on what is the allowed cross-section. There has been a lot of commotion about the various anomalies, but pretty much the status today is that we have only null results and no positive detection, with the exception of gamma. But let's not go into this. And so today we are pretty much probing Higgs-mediated interactions, which are sort of at the 10⁻45 level. Now, this is not the most updated plot. This one neither, but it sort of this is a summary plot from the SNOMAS exercise, which basically shows you a summary of 2 decades of experimental effort of detecting dark matter in direct detection, and all these lines here are either upper limits, and the dashed lines are projections. Some of them actually have already come into being, like Lux and Convex have now the strongest limits. Now, if you want to make progress in this plot, we can do this in 2 directions. Either we probe small and smaller cross sections in the y direction here, and that basically requires bigger experiments, because we need more exposure, more kilogram days. If we want to make progress in the x direction here, to probe lower dark matter masses, then what we really need are lower detector thresholds, and I will elaborate on this a little bit more. Okay, so let's look at the simple kinematics of direct detection. This is a very simple picture, and you know this very well. Dark matter comes into your detector, it strikes a nucleus, and now you ask, what is the recoil energy of the nucleus? So what's the kinetic energy with which the outgoing nucleus flies off? And that depends on the momentum transfer Q here. And so the recoil energy is nothing else than Q squared over 2mn. And so if we have a back-to-back scattering in the center of mass frame, then we have a maximum recoil. And we can now turn this little equation around and say, suppose our experiment has a minimal, an acceptance of it. We require a certain recoil in order to detect the signal. Then this certain recoil demands a minimum relative velocity, and so that's just given here. And so let's say, for example, our detector requires a 500 EV recoil in order to detect the scattering. Then for a 1 GeV particle, what you need is, if you want to scatter if you scatter on oxygen, then you need to have a relative velocity of 600 kilometers per second. If you want to deposit 500 EV on a xenon nucleus, then already for a 1 GeV particle, you need 1700 kilometers per second. And so that immediately tells you that we might be out of luck there, because we believe that the velocity distribution, first of all, the velocity distribution of dark matter in the galactic halo is, to good approximation, Maxwellian. So this here is a Maxwellian shape, but most importantly, it's not a Maxwellian with a long Wien tail, but it's a Maxwellian with a cutoff. And the cutoff is just given by the fact that the galaxy has a finite gravitational potential, and so there's a finite escape velocity, and so it cannot host particles above a certain speed, and this escape velocity is somewhere in the range of 650 kilometers per second. And so if you go back to this equation, now we realize that, say, dark matter has really a mass of 1 GeV, then there is no particle that is bound to the galaxy that could induce, say, a 500 eV nuclear recoil on a xenon atom. And so in a sense, that's a kinematical no-go theorem. We will not be able to detect dark matter particle with a mass smaller than 1 GeV in WIMP nuclear scattering if the detector doesn't have a lower threshold than 500 eV. And so that's the no-go theorem I was alluding to in my title. Now you can ask, okay, well, given the situation, how can we make progress in this plot of dark matter mass versus WIMP nuclear cross section? Because there's a lot of parameter space vastly open, and these are perfectly viable dark matter candidates. Dark matter doesn't have to be 100 GeV, it can also be below the GeV-scale, and that's a perfectly fine possibility. So, of course, people discuss experimental alternatives to this. For example, you may not consider the scattering on the nucleus, but instead you may consider dark matter scattering on the electron, and that's a fair game to play, and people use this scattering to put constraints for dark matter below the GeV-scale. Another possibility is to actually directly produce dark matter in the lab. This goes under the framework of the so-called intensity frontier. So, for example, you can shoot electron or proton beams on fixed targets and produce dark matter directly there. Or there are also a whole number of ideas out there, you know, superconductors using color centers in crystals and whatnot. So there's a plentitude of ideas how we can actually gain access to sub-GeV dark matter, and well, these methods, the time will tell what are prospective proposals there. But for my talk, I would like to propose a different mechanism, and that is simply leaving the elastic scattering and going instead to the inelastic channel. And so what we have in mind is now dark matter scatters again on the nucleus, and now the nucleus emits a continuum photon. So basically it's Bremsstrahlung at this point, and we can just work through the exercise of the, you know, we can just derive the cross section for this and see if there's any prospect that this gets gives us something better. All right, so let's do this. It's very well known that soft photon emission here it can be described by a so-called by a factorized matrix element, where the matrix element for the whole process is just the elastic scattering matrix element times basically a gauge invariant factor. Epsilon is the polarization vector, and dotted into the momentum. K is the momentum of the photon here. It's important to note that this sort of factorization holds for any nucleus, and that's because basically this is a semi-classical process. The nucleus moves on a classical trajectory, and the emission is quantum. So this is really a universal statement here. And so given that the matrix element factorizes, also the cross-section does. And so we immediately obtain the cross-section for this inelastic process here. So it's very simple at this point. All right, so let's compute the cross-section, and here it is. And now the important part is, so again, the cross-section here, now you can see it factorizes. This is just the elastic piece, and there's sort of a cutoff of the maximum photon energy, omega, and times this factor here. Now, importantly, if you look at the maximum energy of the photon, we realize that it is basically the kinetic energy of the WIMP. And so if we compare the maximum photon energy with the maximum recoil energy, we find that for light dark matter, the maximum photon energy wins. And that's the first key why this method actually gives an improvement. So we have a possibility to reach higher energies. The second key is that it's really hard to detect a soft nuclear recoil experimentally. However, if we have a soft photon, then it's basically never missed. And so these are the two key facts which help us to exploit this inelastic channel. Of course, we should make sure that this sort of factorization, which we use here in deriving this cross-section, holds. And indeed, this does, so that the change of momentum transfer delta Q with the additional photon, except for the photon endpoint energy, is always much smaller than momentum transfer itself. And so we can really use this simple picture here. All right. Of course, if we do that, we pay a price going to the inelastic channel costs. First of all, it costs a factor of alpha, so fine structure constant. But actually, this factor of alpha is even overcompensated for heavy nuclei by a coherence factor charge squared. And so this is not the big punishment. The big punishment is a factor recoil energy over nuclear mass. So basically here there's a Q squared, which translates into recoil energy over Mn. And so if you look at xenon, we find this suppression factor is actually enormous, 8 orders of magnitude or 7 orders of magnitude. So now the question is, well, can we overcome the suppression? And the answer is yes, because the recoil spectrum is actually an exponentially rising function with smaller recoil energies. And so we can tap this exponential to overcome the suppression. Maybe I just show you a plot. That's the easiest thing to understand. So here I show you a recoil spectrum now of either nuclear recoil, so the usual thing one is after in direct detection, or now of photon energy. And the dotted line here, that shows the usual elastic scattering spectrum, and it's cut off here for these values for a 1 GeV particle. It's cut off at basically 100 EV recoil energy. It's cut off because there's a escape velocity. And now you see the benefit of going to the inelastic channel, because even though there's a big suppression in the rates, energetically the Bremsstrahlung sort of seeps out of this of the elastic spectrum, and so this part of the spectrum you can now use to constrain these light particles, because the energies go up to here 3 keV, for example. So that's very nice, but we should be a little bit worried, because maybe we have been a little bit too naive about the way of how this photon emission really works. Namely, we have treated the nucleus as being a bare nucleus, fully ionized, and we have derived a cross-section for Bremsstrahlung that actually scales as 1 over omega. So let me just go back. You can see here there's a 1 over omega factor. This is a well-known infrared divergence for soft photon emission. And so if we go to softer and softer photon energies, the whole picture becomes modified by the fact that the nucleus is not bare, but is actually sitting in a bound state with electrons. And so we should really work in this picture where the WIMP scatters on the nucleus inside this electron cloud. And what happens is this is how to understand the process. The WIMP scatters on the nucleus. It displaces the nucleus from the electron cloud, and it creates a dipole here, a dipole between plus and minus, and from that dipole you can emit a photon. In order for this picture to hold, there are some certain conditions which have to be fulfilled. For example, the interaction time of the WIMP with the nucleus has to be rather small, so that this displacement really is not, there's not an adiabatic move of the whole atom, but we really instantaneously shift the nucleus, and then we can actually emit the photon from this polarized atom. But it turns out that this picture holds rather well for our purposes. All right, so this is a fun quantum mechanical calculation which we then did. So we compute now this process of WIMP nucleus scattering in this bound state of electrons, and I here is the initial electron configuration, F is the final electron configuration, and quantum mechanically all intermediate states N are available. And doing this, in the end of the day, what we find is a cross-section where we now get an omega cube factor in front, which has to be there because omega cubed is basically the energy scaling of dipole emission. So the dipole of this polarized atom. So that's very nice. This alpha of omega is not the fine structure constant, but this alpha is something called is what is called the polarizability of the atom. So it's a certain part of this scattering tensor of an atom, and which is there if we consider only the if we consider that the final state equals the initial state. So there will be further contributions to the process if the final state is not the initial state. But if we want to put conservative bounds, we can just take I equals F, and in that case, this becomes here in the cross-section of polarizability. And then we get these usual factors here. Most importantly, and I think this was the nicest part in this whole project, is when we did this quantum mechanical calculation. If you let the energy, the photon energy, go to its endpoint, we actually recover our naive calculation. So the polarizability, the properties of it are such that we just get the c² alpha factor back. It has alpha has a 1 over omega squared dependence, and so in the end of the day, we couple precisely into the naive result. And so that's very nice, and that gives us sort of a confidence that we're doing things right here. Okay, so let me show you this picture again. Now the dotted line was the naive calculation of Bremsstrahlung, and now in addition here we have this this blue solid line, and that's given through the polarizability. And most importantly, this polarizability is something which is tabulated. So we can actually go into the atomic data tables and just read out the values, and we don't have to do any more calculation, but we can make a connection to experimentally infer values. And so now we are sort of really slashed down all the theoretical uncertainties of this process. Okay, so now we have done the important part of calculating that process in detail. Now we need to understand how we can put it to use in direct detection experiments. The first thing to note is that if we emit a photon from the nucleus, it's a so-called electron recoil event, and it's not going to show up in the signal band where one usually expects dark matter scattering to happen, in the so-called nuclear recoil band. Instead, it happens in the electron recoil band, where we have a lot of Compton gammas and beta radioactivity and all these sort of things show up. And so this band is pretty crowded, coming because of radioactivity. And it's crowded here. This is the example of a crest detector. So it's a solid state detector, it's a crystal. And also these crystals have typically KV thresholds. And so this makes solid state detectors currently less suited for this type of search, where we look for this soft photon. Instead, the way to go is to use liquid scintillators. And the reason why, it's because even a very soft photon can induce a signal. The ionization energy of xenon is only 12 eV. And so that's basically all you need, 12 eV, and you can already get a signal. And so if you say inject 100 eV photon, it already produces multiple electrons. And so in principle, this is easily picked up. The electrons are ionized, and then they are drifted in the detector, and it gives already a strong signal. And so it turns out one of the best data are actually also one of the oldest data on this. So this here is the XENON 10 experiment, and in 2011 they put out ionization only analysis. So they throw away the scintillation signal, which is usually much weaker, and they only look at ionization. And here you see their observed spectrum. So this is here the number of 1 electron events, here the number of events with 2 electrons, 4 electrons, 5, and so on and so forth. And so we can use this plot to produce, to put a super conservative limit on our process of soft Bremsstrahlung emission, because if we just take the whole plot here, and we just say we don't care how many electrons are produced in the end, we just bin everything together, we can get a very robust limit by just by demanding that the photon emission rate is smaller than the ionization rate observed in this plot. And doing that, we get this limit here. So now these gray areas right here, those are the existing dark matter limits coming from the elastic scattering. And usually all limits end above a GeV. So now here this is MeV energy. They end above GeV. Only CREST 2, they are the only experiment which put a very aggressive limit down to 500 MeV on dark matter nuclear scattering. But below that, there is no existing limit. And so now we were able to actually put the first limit from direct detection in this mass range here. Actually, we can do a little bit better. I outlined to you sort of the conservative procedure of taking this whole plot in one bin. We can also do a differential limit, and that's something the referees, for example, requested for our paper. Now, that's not online yet on the arXiv, but the revised version will have a limit which makes use of the differential information of how many electrons are produced. And so in our revised version, we consider in more detail the process, the microscopic process, how many electrons are produced upon emission of a photon. And details are not so important here. What is important here is that the limit can actually be improved. And now we go from the 10 to minus 30 level, you improve it by another order of magnitude. And so this here is now the XENON 10 limit. All right. We should still be a little bit worried because these cross sections right here are not too small. 10 to minus 30 versus 10 to minus 36, so smaller. And so it turns out that dark matter may actually start to scatter before it reaches the detector underground. And so if you compute the mean free path, we find that for a 10 to minus 30 cross section, we actually get into the order of the overburden of the detector. And so if we really want to put a precise limit, we should start doing a Monte Carlo analysis of how the incoming flux gets modified and how the incoming energies get modified through this elastic scattering. We did this a little bit. Let me skip over the details. Here what you can see is if you take a light particle and you let it scatter in the Earth, you see how its velocity gradually degrades. So the spectrum becomes softer, but it doesn't do it very quickly, and that's because the energy loss is pretty much suppressed by dark matter mass over nuclear mass. And so the lighter dark matter, the longer it takes for actually the particle will ping around, but it will not lose energy very quickly, and so it takes really a whole number of scatterings before it's soft, too soft to induce a real signal. Here you see how the flux goes down. In any case, for this paper here, for this first paper, we have refrained from incorporating this Monte Carlo analysis into the limits, and we merely say that above 10 to the minus 30 centimeters squared, the limits eventually will disappear. And how quickly they disappear, this depends now on the details of this degradation, and once you do this Monte Carlo, I just highlighted before. But nevertheless, there's a fraction of parameter space which survives. Okay, there's more data. XENON 100 this year put out finally their S2 only analysis. It was a little bit disappointing in the sense that they sort of have a rather high few electron rate in their detector, which this is background which is sort of somewhat poorly understood. But we can still put it to use, and we get a somewhat better limit, but not much better. In any case, what we have derived is now the first limit below 500 GeV, 500 MeV. Now, if you want to go forward, larger detectors might not be necessarily better detectors. So here's, for example, XENON 1 ton. And the reason is everything depends on the background rate, really. But a low background rate is only achieved in the fiducial volume. So that means only in a sort of in a core region of the detector, which is far away from photomultipliers and all that. Now you can ask, how do you actually fiducialize? And the way to fiducialize is by observing the scintillation signal. So you see two photons flying off, and that gives you the ability to construct the position of the event, and that allows you to say if it's in the fiducial or outside the fiducial volume. So these small rates require actually the scintillation signal. And so it very much depends how good your detector is in picking up the weaker scintillation signal in order to make use of the fiducialized rates. Let me skip over the details here and just show you our projections for sort of an experiment, a liquid xenon experiment where we require scintillation and where the detection efficiency of these photons, of each of the photons, vary between 40 and 100%. 40% is what the best detectors do right now. 100% is a very futuristic, and sort of this gives you sort of the, I would say, the most optimistic reach of this technology when we want to exploit the inelastic channel. On the other hand, actually, it turns out that CREST, so the solid-state detectors, might do better. So CREST, they produce now their own crystals, so they're homegrown, and they promise us very low radioactive rates in their crystals. And so, using their own numbers from their paper for projections, we actually get this line here. And so, this is something interesting to do for them. I should note that even if CREST lowers the threshold here, they might get better in their limit with the elastic scattering. But the recoil energy in the elastic signal, it decouples with mchi squared, whereas the kinetic energy of the WIMP goes linearly with mchi. And so there's always a region that Bremsstrahlung will win over the elastic channel. So even though this picture might look different in the future, there will still be a region where the Bremsstrahlung will be the best probe for low dark matter masses. Okay. I think I should talk half an hour, so I'm a little bit over time already, so I'll be a little bit quicker over the rest. One important thing is we should actually compare our proposal to dark matter electron scattering, because constraints have already been put on sub-GeV dark matter from dark matter electron scattering. And if you look at the numbers here, what are the cross-sections which are constrained? We find that basically we can only get an improvement over the dark matter electron scattering limits if dark matter electron scattering is suppressed at least by 6 orders of magnitude relative to dark matter nuclear. If dark matter nuclear scattering wins over dark matter electron scattering by at least 6 orders of magnitude. And so naturally we are drawn into so-called leptophobic dark matter models, where dark matter only scatters on the nucleus but doesn't scatter on the electron. And so let me just show you the most vanilla simple model of a leptophobic dark matter model, which you can build. You can take U1b, gauged baryon number. V would be the vector of this new U1 group. And you can have a fermionic or scalar dark matter particle, which then has gauge interactions of this new U1. So dark matter interacts with the baryon current essentially. So Q bar Q is the Q bar gamma mu Q is the baryon current. And yeah, so these sort of leptophobic models have been entertained a lot in the literature, and so we can just put them to use for our purposes. However, what is important, even if the kinetic mixing of with the ordinary photon is 0 at tree level, it might be induced radiatively, and so radiatively we can actually generate dark matter electron scattering even if we had it turned off on the tree level. And so just think of this process here. We have the ordinary photon, and here we have our gauged baryon number. Quarks can run in the loop, and they induce radiative kappa here. And so if you look at sort of the parametric estimates, we start out with scattering on the nucleon. We have this value here, and then there will be the scattering on electrons. It has an additional factor of kappa squared, alpha times alpha b versus alpha b squared. So alpha b squared is sort of the baryonic coupling with a kappa that is radiatively induced. So it's on this order. And if you compare these cross sections now, we actually find that indeed we can achieve this hierarchy between elastic and between electron and nucleon scattering. And so our method works and we win. Maybe just show you a plot instead. Here in orange, this line here is the Bremsstrahlung emission. This is now the theory rate. So this is the rate in XENON as a function of gamma energy. It's given here. And in blue, smaller, is the rate of electron scattering with a radiatively induced process. And most importantly, the gamma energy is sort of higher, so it has a higher endpoint energy. And so when you start to fold in the electron multiplicities, etc., so if you work out the detector signal, this here will be a much stronger signal than this blue one here. And so indeed, we can cover new territory here. Finally, there can also be constraints from the collider here from monojets. This has been worked out in the literature, and we can use these limits to put them on our plot as well. In the end of the day, the upshot is we have nice new limits, and we break new ground with these things. And so let me conclude and provide some outlook. I've shown you that that already existing as well as upcoming direct detection experiments they can constrain a region in dark matter mass which has been thought to be inaccessible, namely the sub 500 MeV mass region. And we break this kinematical no-go theorem from elastic scattering by going to the inelastic channel of photon emission, which has the benefit of having a higher endpoint energy. And I've shown you, I've proven the existence of models that we can actually constrain better with this method. I should also say there's a whole number of ways how we can and will actually improve our limits on this first proposal. So for example, we should look at not only the photon emissions channel, but we should also look at the direct shake-off contribution of electrons. So you kick the nucleus, some electrons fly off, and so this is sort of a soft signal. And we should also include higher atomic final states. I've alluded to this briefly in the talk. We should look at the spin-dependent case. We should work out the analogous signal in a semiconductor versus which has a very different electron band structure, and so the signal formation might be different. And finally, we should also reevaluate the neutrino floor given this new signal here. Thank you very much. I should switch back now to my camera. I hope you're still all here. Hello?
Hello.
Hello.
Hello, can you hear me?
Yes, I can hear you. Hello?
Host has a problem, so now I'm gonna be host for now. So anyway, so
okay.
Thank you very much, Joseph. It was very, very nice, the talk. I like it a lot. So maybe just to remember to the people that is following now the webinar, that they can make questions via the YouTube chat. If you're following this live, you can make questions. You can make questions for Joseph directly to him. But now we'll start with a question from the public that is here in the session of the Hangout. So please, if there is someone with a question, we can start now. So.
Oh, I have a very hi. So your issue with the cross section was involved the rescatterings with the shield, right, of your detector, right? So would you suggest in that case removing this shield, decreasing the shield? How would that affect your backgrounds for those searches?
I think no. I was maybe I was not entirely clear on this point. So if you look at the projections, say from XENON 1 ton. Okay, so XENON 1 ton, they are trying to reduce their electromagnetic background by a lot, and so they give us rates which are between 1 or even 2 orders of magnitude lower than in their current detector. So they say they will, so this is a reduction of electromagnetic background by a large factor. And you can ask, how do I go to these small rates? And you can only do it by taking, by fiducializing your detector volume, because on the outer exterior, where the photomultipliers and just the usual components of the detector sit, they are dirty in a sense. So they have a lot of contribution to the background. And so as soon as you can start localizing where your event was, you can cut out all the crap. But that localization requires scintillation, and scintillation is a weak signal, and it requires sufficient energy deposition. And so that's why just making a bigger detector and having smaller fiducialized rates does not necessarily gain you a lot in our proposal. And so it depends a lot on experimental details, and we have tried to quantify them to some degree. And well, yeah, it's
okay. I see. Thanks. Yeah.
Thanks.
So there is another question. I have a question. Just while the people start to prepare questions. Yeah. So when you were explaining the model, the idea of using the photon, I was wondering if it is. Do you expect to have also effects like spin-dependent cross sections? Because at the moment you just compare with the spin independent with the coherent scattering of the from the emission from the photon. But I was wondering if there is some effect or different observable depending on which part of the nucleus is emitting the photon. In principle, it should be only the proton if it is.
No, so there you don't have to worry about any nuclear form factor of any sort. So we are also not considering the emission of a photon because of an excitation of the nucleus. So I should maybe more generally answer there are various ways of emitting a photon from a nucleus. One way is the WIMP scatters pretty strongly and you go into an excited state of the nucleus, then it de-excites and it emits a photon. These things have been looked at, but it requires quite sizable momentum transfer. And you can only go into excited state using heavier dark matter. So you need WIMP dark matter, and then there are certain xenon isotopes which have 30 keV low-lying nuclear levels, which you might hope to excite. This is one possibility, but this is not what we look at because we look at very light dark matter. And so you never go into an excited state. And now there, you never need to worry about things like flipping a nucleon or any of this sort, because the photon is relatively soft, and so you never probe the inner structure of the nucleus. So this is basically a coherent emission with a factor of c². The photon energies go, it's at most a keV, and Fermi scale is 200 MeV, so you have a very soft photon with respect to the size of the nucleus. You never resolve any of that. But since you mentioned spin-dependent, what is interesting in the spin-dependent case is that there are certain operators where you can couple to quarks, and you never generate a coupling to electrons on no loop level. So, for example, this is the that's axial vector coupling, but it's also velocity suppressed. But in principle, I think what we should do is take our proposal and also look for the spin-dependent case, because indeed there are really cases where you don't induce any scattering on electrons, and then Bremsstrahlung will be the only way of going to lower masses. Did this answer your question? Or?
Yeah. In fact, it was very enlightening. So, just the other extreme. When you were in your plots showing like a lower limit of, if I remember well, was kind of 50 MeV, something like that, 10 MeV.
I can turn on the. You want me to turn on the?
Yeah, if it is possible. Yeah.
Yes, sure. I go.
No, my question was in the point of which is would be your no-go theorem for this method, in the sense, because at some point your no-go was the minimal recoil energy that can be detected in the
yes
detector. I mean,
that's
what would be your no-go theorem?
That's a great question. So that actually depends on what's your method of detection. Say, for example, we look at this liquid scintillators, and if you look at this liquid scintillators, what you require is ionization. So the minimum energy of the photon is 12 eV, because that's the binding energy of the most shallow bound electron in a xenon nucleus. So that's the n = 5 shell. There's some electrons with 12 eV. So that's the minimum energy you need, and that energy. So 12 eV would be the minimum kinetic energy of the dark matter particle you need to have. And so now you convert. Now you take m_chi v² half equals 12 eV, and you find out what's the dark matter mass. And so it's I don't know. It's somewhere in the MeV regime. I don't know the exact value, but that would be the answer. But it's also possible that you are going lower, and you say, "Oh, actually, I don't require the ionization signal, but you can directly try to detect this photon. So below 7 eV, liquid xenon becomes transparent. And so it's like liquid xenon is transparent to scintillation, so it's transparent to its own scintillation light. That's why you can detect it. And so in principle, you can also try to be more ambitious and look really for the super soft part of the spectrum directly. Not easy. I mean, we have some ideas. I'm not sure what is going to work in the end, but yeah, we are thinking of this. Yeah.
Okay. So, and just the last question for the moment is what about the experiment with annual modulation? Do you think that they could also try to use this method?
Yeah. So I don't have my bonus material. I made so there's you can ask what you can do is you can ask, for example, take gamma and you can speculate that maybe the modulating signal is not due to wait, you know what? Maybe let me pull up a slide and show you. I have a different talk where I have this. If you can just wait. Okay, so. Oops. So what I need to do is screen sharing again, and then I can show you the plot. Do you see my screen?
Yes, we can see it.
Okay, very good. So, oops.
Okay, it seems that the host, I mean the speaker went out. Maybe he went to look for the slides to the next office. But for the moment that he's coming back, just to remember to the people that you can make questions to him. You can start to write a question to him in the YouTube chat live. For the moment that he's coming back, you can also remember to subscribe to our Facebook page. And if you enter to the WordPress page that we have, there is one of the menu that is to subscribe to the mailing list in case that you want to receive all the announcement of the webinars and just a reminder just before the beginning of it. So you can write there. So for the moment that he's connecting back, also we can, I don't know if you were planning to make questions to them, because it seems that also, yeah,
we had a question.
He was gone. You have a question for him?
Yes, but for him.
Not for me. No, yeah, let's wait for a moment. So I guess the people can wait a couple of minutes, because the most probably that if you notice that when he turned down his laptop, it seems that maybe he disconnected the cable of his computer. Now it's coming back. Yeah, great.
Hello.
Hello, Josef.
Hello. I'm sorry. Did you hear any? Sorry, I think I hit the quit button on the wrong. Did you hear anything from what I said?
No. It's remaining a secret, the solution to the annual modulation.
I think maybe that was engineered. No, okay, I'll show you. And I will make it very quick. Sorry.
No, don't worry.
Okay, wait. Okay, so here it is. So you can hypothesize that dark matter, that the annual modulation is not induced by elastic scattering, but from the Bremsstrahlung part. Of course, there's also a modulated part of the elastic scattering, but that happens at a lower energy. And so we assume now that it's not detected. Only the harder part of the spectrum, which is the Bremsstrahlung, makes it into the detectable region. And that's what indeed is observed. And so here I went through the exercise of fitting the gamma signal through this Bremsstrahlung, and that's it gives a very nice fit, good chi-squared, all of this. If you look in the bigger context where this island shows up, You see it right here. So this here is now a third Dama island. There are these two islands down here somewhere at higher dark matter masses. And now there's this here is the island coming from Bremsstrahlung. Had we proposed this a number of years back, this would probably be very exciting when these limits when the other limits were not in place. But now it's actually, this possibility is excluded. So yeah, it was a fun exercise, but I don't think it has anything to do with Dama.
Okay, so there were now we hear that Nicolás has questions.
We are back here. Can you hear us?
Yes, I can hear you.
Yes.
Okay, sorry. So I have a question about the directionality. Can you use this to reconstruct the direction of incoming dark matter?
Yes, it's a great question. It's something we are thinking about, and we think it might be possible. It's not easy. So the directional there's a directional dependence in the photon emission, and that is you basically dot Q, so the momentum transfer, into the polarization vector. That's the information you have. Okay, and so there's a certain there's a preference of emitting this radiation, yeah, orthogonal to the direction of the wind, if you want. And so there's some information there. You may try to correlate it with the recoil energy. And we are currently looking, tossing various possibilities around of doing this. I don't think it's easy, but if you go to low photon energies, again, what I said before, XENON becomes transparent, and you may actually try to do this. But
maybe not photon
so
by
we
photon.
have the cross. Sorry.
Maybe not photon by photon, but statistically you can try to.
Of course, yeah, no, this is statistically, yeah, but yeah, so we have all the formulas. We have to put the things together now. I mean,
So do we have other questions for Joseph? I guess the time is, we already arrived to the hour of transmission. So I guess it was a very, I'm going to check if we have questions in the chat. It seems, no, we don't have questions there. But anyway, for all the followers of the transmission, you can watch again this webinar in our YouTube channel. So I guess for the moment we are going to thank Joseph for this very nice seminar and the idea that was very good to explain. And I guess just to tell to the rest of the people that is following us is just to tune us again next week. We are going to have another webinar from Pablo Royce from Simvestab, Mexico, and I hope you see you again next week. So, goodbye.
Thank you very much.